So before we go deeper into convolutions, let's talk a little bit about image data and its challenges. And we start with a question. The question is, can we actually use multilayer perceptrons on image data? The answer is yes. So here we have a grayscale image with 14 × 14 pixels. And we will shrink this image a little bit to make it better fit onto the slide. Now, in order to use this image as an input to a multilayer perceptron, what we can do is we can concatenate the rows. So we have 14 rows, and in order to use it as a feature vector, we can concatenate those. And the concatenation looks like as follows. So after concatenating all the rows, we now have a 196-dimensional row vector. So this row vector represents the feature vector for a single training example. So the training example corresponding to the digit 2 that we have just seen. So we can then do the same thing for a second training example. So here suppose we have the handwritten digit 6. So again, this is a 14 × 14 dimensional grayscale image. And then because it's so much fun, let's do it one more time with the digit 8. So here we have a digit 8 as a 14 × 14 dimensional image. So carrying out the concatenation for each of these images will result in a 196-dimensional feature vector for each of the 3 images. So consequently, our dataset, our tabular dataset, now consists of 3 rows and 196 columns. So this concatenated image dataset is essentially analogous to, for example, this iris dataset here, where each position represents one feature column in the dataset. And by the way, as a side note, when we work with image data, each pixel value is a value, an integer, in the range between 0 to 255. You may remember that we already used the multilayer perceptron on an image dataset. So in fact, we applied this multilayer perceptron to the MNIST handwritten digit database. So in the MNIST dataset, we have grayscale images with 28 × 28 pixels. So in the concatenated representation, each training example consists of a 784-dimensional feature vector. And by the way, we can carry out this concatenation of the rows in each image very easily in PyTorch by just using this flatten function. So by using flatten, PyTorch will convert the 28 × 28 images into these 784-dimensional feature vectors. And this way we can then use a multilayer perceptron for image data. In fact, for this MNIST dataset, using a multilayer perceptron works actually pretty well. As you can see here at the bottom, with this multilayer perceptron, we can achieve 96% accuracy on the MNIST dataset. But of course, this is only a very simple dataset. However, multilayer perceptrons unfortunately don't work very well for more complicated image classification problems. So one of the reasons is that multilayer perceptrons heavily rely on certain pixel positions. So suppose, for example, we have the following example of the digit 1. And the multilayer perceptron relies on the highlighted pixels here in order to classify it as the number 1. So now consider this digit 1 that is slightly off center. In this case, the multilayer perceptron will look at the wrong place in order to classify it. And now here in the place where it looks at, there are no pixel values that are corresponding to the digit 1. So in this case, it will not make the prediction that this is a digit 1. Another issue with multilayer perceptrons for image data is that the features are considered independent in the multilayer perceptron. So it considers each feature as an independent feature. Convolutional networks, on the other hand, will also take locality into account. So given a pixel, it will look also in the surrounding area and make the decision based on local regions in the image, not just individual pixels. And so this is in a nutshell what's so challenging about working with image data. In the next video, we will take a look at the convolutional neural network architecture, which is specifically designed to work with image data.